Good morning or afternoon, everyone. We are finally going into the last kind of topic that we will be talking about in this class, and that is going to consider radical expressions. We are talking about radical expressions, and we are going to do a similar thing to what we have done with rational expressions. We're first going to look how to simplify these. Then we are going to look how to multiply and divide, and then we are going to look how to add and subtract these expressions. The difference from rational expressions, we will not look at radical equations in this class. That we will save for college algebra. All right, let's get started. So if I have something that looks like this here, then we are going to say up here, this n, this is called the index. This sign here, this weird kind of sign, this is called the radical sign. Whatever is underneath the radical, that is called the radicand. And this whole thing together is called a radical expression. Remember, or let me tell you that this index does not need to be written down if I am only talking about the square root. So in other words, if there is a 2 theoretically being the index, then I do not need to write this 2. This is the same thing as if I would just write this. So let's have a look at what this really means. We are going to say, and this is a little bit definition at the beginning, that the square root of a is equal to some number b. This is equal to some number b if and only if this number squared was equal to the inside, to the radicand. To make this a little bit clearer, let's look at some examples. Also, this inside right here, this has to be positive for us if we are looking at square roots. So let's have a look at the first one, the square roots of 9. The square roots of 9 is equal to 3. Why? Because 3 squared is equal to 9. You always have to ask yourself this question right here. The square root of 81 is equal to 9. Why? Because 9 squared was equal to 81. The square root of a negative 16, oh, hold on, you cannot do this. This is not a real number. First of all, because it is not positive, the radicand is not positive. Second of all, you cannot find a number that you multiply by itself to get negative 16. If you are trying 4, then you get positive 16, and if you try negative 4, then you will still get a positive 16. So whenever there is a negative number underneath the square root, that will not be a real number. Let's have a look at some more examples. The next 2 examples are going to demonstrate something very important for us. Let's have a look. So, the square root of 144 plus 25. Let's have a look. What is 144 plus 25? That's 164. That's 169. All right. And the square root of 169, let's have a look. That is 13. And why is that so? Well, because 13 squared is equal to 169. That's why. Let's have a look at the next one right here. The square root of 144 plus the square roots of 25. The square root of 144, now that is 12. The square roots of 25, that will be 5. And 12 plus 5, that is 17. Now we have just discovered something very, very important. That for addition, it makes all the difference in the world when I add. We are going to see that there is something slightly different happening with multiplication. underneath the radicand, you first have to add. If you add the radicands like this, then you can first do this, and then the square roots of 25, and then add the numbers. You see that you will get something different in both ways. This is not the same. Let's have a look at the negative of the square roots of 49. We said something about negatives, but this is a slight little bit different because not the radicand is negative, but the negative is on the outside. You can think about this as this. This is a negative 1 times the square roots of 49. And the square roots of 49, that is 7. So I will get overall a negative 7. So I can get negative numbers, but only if the negative sign is on the outside of the radical sign. All right. Now we are going to look at some special cases. The square root of a squared is equal to the absolute value of a. These bars right here, these mean the absolute value. The absolute value. And the absolute value is always positive. So the square root of 4 squared, according to this rule right here, is going to be the absolute value of 4. Well, the absolute value of a positive 4 is still 4. Look, if I would have gone the long way, then I could have said the square root of 4 squared. What is 4 squared again? That is 16. And the square root of 16 is indeed 4. So, in other words, this right here is just a shortcut if I have it in this special form. So in my next example, the square root of a negative 3 squared, according to my rule, is the absolute value of a negative 3. And the absolute value of a negative 3 is a positive 3. Again, if I would look at it the long way, what do I get when I multiply underneath my radical sign out? A negative 3 squared is a negative 3 times a negative 3. That's positive 9. And the square root out of a positive 9 indeed is positive 3. So this rule works. Let's go ahead and simplify something that, some expressions that look already a slight little bit more complicated. The square root of 81x squared. So what we are always going to do if I want to simplify, we are going to rewrite if possible. And the best way, if I can rewrite it like this. The square root, remember that there is theoretically a 2 standing up there. So you will be able to think about that these 2 can cancel out, and then I will get the absolute value of whatever was inside my parentheses in here. So what do I have to put in here so that if I go backwards, I will get 81x squared again? That will be 9x. 9x squared is the same thing as 81x squared. So in other words, now it's just a matter of writing it down. The answer is the absolute value of 9x. If I do the same thing with this second example, I have already a perfect square. I have already this parentheses with the square on the outside. So in other words, I only need to focus on this inside, the x plus 8. Now, because this is the square root, I'm going to get the absolute value of x plus 8. All right? This is not the same thing as if you would write the absolute value of x plus the absolute value of 8. Don't do this. This is not the same thing. If you would plug in some negative numbers in there, then you will see that you get something different. All right, let's do some cubic roots. Cubic roots, so we're going to slowly back up with the numbers in the index, in the indices. The cubic root of a is equal to b if and only if b cubed is equal to a. So this is almost the exact same thing as before, but this number underneath here does not necessarily need to be positive. For instance, the square root of a negative 27, that is negative 3. So in this case, I can get negative numbers. Why is it negative 3? Well, because a negative 3 in parentheses cubed is in fact equal to negative 27. All right? So here is the rule from before. We had just a moment ago that the square root of a squared was equal to the absolute value of a. This too we didn't need to write. Now we have the same rule for cubics. The cubic root out of something cubed is equal to a. Notice that I do not need any absolute values around here because this can be negative, as we have seen in the last example, or as we see now in this example. The cubic root out of 4 cubed is equal to 4. If you would go the long way, then you would write, this is the cubic root out of, well, what is 4? 3 times multiplied by itself. That is 64. 4 times 4 is 16, times 4 is 64. And the cubic root out of 64 is indeed 4. So this right here is just the shortcut if I have it in this special form. The same thing works in this case. This is just a negative 4, not the absolute value of a negative 4, because if I would go the long way, well, what is a negative 4 times negative 4 times negative 4? That is a negative 64. And the cubic root out of a negative 64 is negative 4. Why? Because a negative 4 cubed is negative 64. So we are going to go a little bit back and forwards here. Let's go ahead and simplify one more expression before we go yet higher with our indices. The cubic root out of a negative 27x cubed, what we are going to do, I am going to rewrite the radicand, and I'm going to rewrite it so that I have a perfect cube. And I can do this by plugging in a negative 3x in here. Notice that a negative 3x to the third power is negative 27x cubed. These were the rules of exponents, and this is why we had to talk about those ones beforehand. Now I can just open up this whole radical, and I get the negative 3 times x. No absolute values necessary. You may think about this like this, that this 3 and this 3 is kind of canceling each other out, which really is what is happening here, but we will have to wait a section to see why this is so. Now, let's go higher with the radicals. Excuse me. If n is even, then I get that the nth root out of a to the n power is the absolute value of a. If n is odd, then I get that the nth root of a to the n is just a. What does this mean? Well, let me give you an example. N even, an even number, 4. 4 is an even number. So if I have now inside here a negative 3 raised to the 4th power, then according to this rule, because 4 is even, I will get the absolute value of a negative 3, which is positive 3. If I were to look at the 5th root out of a negative 3 raised to the 5th power, now we have an odd root, and that will give us just negative 3. For those of you who are curious, negative 3 raised to the 4th power, that would be 81. This is a positive 3. And negative 3 raised to the 5th power, that would be 243, but a negative 243. And that would give us a negative 3. So these rules do indeed work. Let's do a few examples for these rules, and then we will be done for today. The fourth root out of x plus 6 to the 4th power. No work needs to be done. I have a fourth root, and I have it to the 4th power. These are even root, radicals, and that means that the answer will be the absolute value of x plus 6. That's already it. In my next example, this is the 5th root out of something to the 5th power. Now I'm just going to get 3x minus 2. No absolute values necessary. This is already the answer. Next time we are going to look at how to do not perfect squares and cubic roots and all of that.